All right, I'm sorry for this miscommunication, but this is actually an error. I guess I was fairly distracted, and I got the chemistry wrong when I explained this in the last video. So, just to be clear, when you have iron, iron has three what we call valence electrons, or three electrons in its outer shell that it really would like to get rid of. And oxygen, when you look at oxygen, oxygen has 1, 2, 3, 4, 5, 6 in the outer shell, and it can form. In oxygen, what it wants to do is grab 2 electrons so it can fill these empty spaces. The objective of most atoms is to get 8 electrons in the outer shell. This has 3. Iron gets 8 by getting rid of the 3 in the outer shell, and the inner shell has 8. I know that we haven't covered this yet, and that's why I really didn't want to get into it, but I wanted to make sure I get the chemistry straight, and then we can go into details next week when we cover this component of chemistry. So when you're looking at this atom, so when you're looking at oxygen, a molecule of oxygen, what you're looking at is that the outer shell is sharing electrons, and these two are getting shared, and these two are getting shared. And if you think about sharing, that means that both of them get the electrons, right? Because that's what sharing means. You both get some. So here's 1, 2, 3, 4, 5, 6, 7, 8 electrons around this oxygen. Here's 1, 2, 3, 4, 5, 6, 7, 8 around this oxygen. So that satisfies their need to have 8 electrons in the outer shell. Now with iron, you'll see this oxygen needs 2, and this iron needs to get rid of these 3 electrons. It's a complicated discussion I don't want to have right now, but what will happen is that, oops, let me get rid of this, that this oxygen and this iron, the electrons, let me put that here. This iron's going to give 2 of its electrons to an oxygen, but then that leaves you with 1 that needs to be gotten rid of. So what happens is another oxygen comes in and takes that electron. But then that leaves oxygen, this oxygen without an electron. So we need another iron. Let me move this whole thing. We need another iron atom so that it can give an electron to that oxygen. So now if you look at it, this oxygen has 8 electrons, this oxygen has 8 electrons. This iron's gotten rid of those 3. This iron only got rid of 1. It has 2 more to get rid of. But luckily, if you take another oxygen, it will take both of these electrons. So the actual formula for iron oxide is iron 2O3, FeO3. So to be clear, the reason that the formula for iron oxide is actually Fe2O3 and not FeO3 is that there's 2 irons. In other words, 2 irons are required to take up 3 oxygens. 2 iron atoms are required to take up 3 oxygens. And that's because these electrons, because of the number of electrons that are needed to be transferred and accepted. So the only way you get 8 around to get each oxygen to have 8 electrons and get rid of all 3 electrons in the outer shell for the iron is to have 2 irons combining with 3 oxygens. So this combination is what we call a formula. And this is the formula for this ionic compound. Now, you don't know what an ionic compound is yet. You're not sure. I know you don't know the rules of how these atoms all combine and how and what you don't even know what an electron is. We'll learn about all that next week. But I just wanted to be clear that there's reasons and underlying causes for this chemical reaction to occur. And we'll get into the details and the hows and the what fors next week, as I said. We're not going to get into extreme detail because this is a biology class and not a chemistry class. But it's important that you understand that electrons, the movement of electrons, the sharing of electrons, is all of that helps determine how substances change. And it's important that you understand that the changes that occur, when they occur this way with the sharing or exchanging of electrons, and the substances change their characteristics, we call that a chemical change. And that chemical change is when you rearrange the atoms that are bonded together. And when I say bonded together, whenever anyone ever says two atoms are bonded together, what they mean is that they're sharing electrons. Electrons are being shared. That's what a covalent bond is a sharing of electrons. You can give away electrons the way you see here. Iron is giving away the electrons to oxygen, but that creates an ionic compound. So this is an ionic compound. In other words, these are associating with each other, but they're not very strongly associated. So if you put them in water, they'll dissolve easily, right? So they'll break apart. They'll become ions. And becoming ions means that they become charged. And since they're charged, they'll dissolve easily in water. All that will come in time, so I don't mean to overwhelm you, which is part of the reason they want to get into it in the lab. But it's necessary for you to understand some of the underlying causes of why the oxygen is removed from the air. So gas oxygen looks like this. It's O2. But when oxygen gas comes into contact with iron, especially under acidic conditions, right, and in the presence of water, we know that. We know that this oxygen will actually react with iron and form a rust. That rust is iron oxide. That's because the oxygen gets taken, they break apart. These two oxygens that were bonded break apart. That oxygen goes and bonds with the iron, and you form this new substance. So this used to be a gas, and now this is a solid. Now things change, and this is going to be a tricky point, and I know it might be a little much, but I think it's important. It's an opportunity here to say that this is a change. This particular example of an oxygen gas combining in a chemical change to form a solid, you'll notice that this was clear. It's a gas. This was a solid. So you combine two things, a gas with a solid, and you formed a third thing called a solid. You know it's different because it's red. You know it's different because of, in other words, you know it's different because of a color change. You know that it changed state. In other words, it changed from gas to solid. It became brittle. It can now dissolve easily and dissolves in water. The solid dissolved in water where the solid iron didn't before. So these are important properties that changed. There were clues. These were clues that you had a chemical change. Now, what's interesting is that the changing from gas to solid is not a chemical change. In fact, it's called the physical change. Someone asked in class the other day, just yesterday, they said, wait a minute, you said gas water. Is there such a thing as a gas form of water? So yes, actually there is. So if you have H2O, H2O. It looks like this, an oxygen with two hydrogens. That could be a liquid. As you know, we drink it all the time. Or it could be a gas, right? So there's water. This same molecule, same arrangement of atoms, can be a gas if there's enough energy. If you heat it up enough, you can get these molecules to separate and go flying in every direction. But at room temperature, it's a liquid. Water's a liquid. But if you make it colder, you can turn water into a solid, right? We can call that ice. So we can freeze it, we can boil it, and boiling is at 100 degrees Celsius. Freezing is 0 degrees Celsius at 1 atmospheric pressure. And that freezing, the water is still H2O. The gas is still H2O. So water is water, whether it's gas, liquid, or solid. All right. And you should know that in the opposite direction, that same water, just by changing temperature or pressure, you can have that water condense, or you can have that water melt. Now, what I find interesting is that the melting point and the freezing point are the same, and the boiling point and the condensation point's the same. Water condenses at 1 atmospheric pressure, and there's other factors, but water turns back into a liquid at 100 degrees Celsius. Water freezes at 0 degrees Celsius, but it melts at 0 degrees Celsius as well. So we call that phase change, and phase because that's the phase or state of matter. So this phase change is a physical change. So when you boil water or melt it, you're not chemically changing it. So what's the difference between these two situations? Situations 1 and situation 2, where one you have a chemical change, the other you have a physical change. Now, if you notice, both of them have a gas going to a solid, right? A gas going to a solid. If you froze gas water, froze it instantly. And I think you've seen that where people take boiling water and they throw it off. Don't do this. Do not do this. But you've seen these in YouTube videos. It's common. They boil the water and they go on a really super cold day and throw it up in the air and it goes right to a solid. It doesn't, that gas turns right into a solid. Also, another good example is sublimation, right? Where you go carbon dioxide solid goes right to gas. So in any case, you don't have to go from gas straight to solid, but if you see that we're having a phase change, gas water going to solid water, or gas water going to liquid and then to solid, this is a phase change. It's still a physical change. Well, this was a phase change too, went from gas to solid. So what's the difference between situation 1 and situation 2? Well, if you look, this is water, H2O. This is water, H2O, and this is water, H2O. The combination of atoms, right, the arrangement of atoms did not change. But up here, the arrangement of atoms changed, where you had oxygen combining with iron solid, oxygen gas, combining with iron solid to form this other material called iron oxide. So when you're contemplating the difference between a chemical change and physical change, just remember it's just a rearrangement of atoms. When you're contemplating how is it that the iron removed the oxygen gas in the experiment from the test tube, it's because you had a chemical change or chemical reaction, and the iron bonded with the oxygen, chemically bonded with the oxygen. They exchanged electrons. All right, so that's it. It's only 15 minutes, thank God. I think I went in in depth enough that it should be helpful. I'm sorry I made a mistake. It was a very confusing day yesterday and a lot of stuff going on, as I'm sure you can tell from the video. We will we'll continue this this week, and next week we'll get deeper into chemistry. All right. Have a good weekend, or have a good evening.